I work for a pharmaceutical company, AstraZeneca. I'm an associate principal data engineer there. I work in biopharmaceutical R&D, so we develop tools that potentially help R&D, actual drug developers or researchers invent new drugs. But this talk is not about that. So it's about building game-like or Doom-like world to explore agentic systems. So I'm not a game developer or engineer or programmer. Yet I find this topic fascinating to explore idea. What can we do about agents? How we can build agents? How the game can be a platform to try agents. So it's what I'm building here is agents as a semantic mirror of the game world. So there's such definition in the available today called digital twins. So we actually can construct any system, real-life system built into the agents and replicate the system, model it, and use it to understand better phenomena. We can run simulations, we can run models with that approach. So it's kind of similar, except it's semantic mirror. So we're trying to not to rebuild entire Doom in agents. What we're trying to do is to understand semantics of the game and trying to replicate in agents. So it's a bit smaller scope, but very similar to what is actually in digital twins intended. So we talk about architecture, observable actions, and two-tier agentic vision demo. So I hope that demo will work. So what we will talk about is part one, maybe 10 minutes on why game engines are used for environment for agent work. So there are control loops, states, real-time feedback. Part two is about it's about long stretch. It's about 25 minutes on architecture, so world state, perception, decision loops, observability, invariant. And part three is about 20 minutes is implementation. It's finished state agents in Z script. This is a script for Doom. The policy guard, MCP gateway, agent cell adapter, and how the multiple agents coordinate. And part four is closing. It's 5 minutes, and we'll talk about how to transfer this kind of implementation to production agent systems, how they relate to one to another. So just to start with what we think the agents are. So the agents are, in a software sense, is autonomous entity that perceives the environment, makes decisions. So it has, it's actually it's a long-standing concept from 40s, 50s, 60s, 70s, and so on, as you see. But key characteristics of the agents is that it has autonomy, perception. So Census API have goal-oriented planning, have proactivity, have social ability. So agents can communicate to another agents or to humans. And we certainly have now modern LLM agents that use large language model as reasoning core supported by the memory modelers and tools. So APIs and browsers. So it's additional layer since 2 or 3 years, but agents as concept existed before. So, and this is what I'm talking here about. So what we're going to do, we're going to work with a game. So I'm not affiliated, obviously, with GZ Doom or JX Doom or whatever development. I'm not affiliated also with Project Brutality. So this is actually an investment in looks and feel of the game and so on. So, and it's actually kind of have a bit graphical content, but it's actually similar to what you may see in movies like Day of the Dead, Dawn of the Dead, or something like that. So, we're going to play this shortly during the presentation, and I'll show you where actually agentic behavior appears. So it's actually totally movable, as you see, totally fine. So we also will be talking about how to make control plane. So it's actually an idea that there are interconnected elements in this game, components that talk to each other. And those are agentic components, and we'll go through details, how it's all implemented and how it works. Even so, probably would not be too much programming, but again, it will be interesting. So back to the demo. So the idea, agents as semantic mirror of the world, is that we don't simulate the game and the world from scratch. The agent already does that. It does that. Instead, we mirror it. The mirror has 3 tiers. So tier 1 is structural mirror. So where one observer finite state machine for every visible actor, position, health, face, no LLM. It's around 7 hertz. So actually, we building agents in certain sync. That's shape of the world. And then tier 2 is semantic mirror. So it's a small number of per-lens LLM brokers that attach labels like shotgun, dude, danger, low ammo, and so on. Sparse, expensive, cached. This is our interpretation of the world. And tier 3 is behavior. So 1,000 agent consumers. So we have 1,000 agents here. So not necessarily all of them running ALM, not necessarily all do some, but they're all related to reasoning, actually. So we have 1,000 agent consumer swarm that reads the mirror and acts it through the MCP. And contribution isn't the doom. The contribution is architecture. So how we build it and how we make it work. Okay. So why game agents? So the challenge with AI agents are not traditional software. Their behavior emerges from interaction with the environment. Not just deterministic logic. It's not just a piece of software where put if then. It's actually much more complex there. And so it has no deterministic reason because it's LLM behind. LLM may decide one way or another. It has long decision chains with cascading effects. And it has emerging behavior from multi-agent interaction. So agent can talk to another agent to construct much more complex behavior. And also has environment-dependent outcomes. So the question is how we design, test, and govern agent behavior before deploying to a real system. So we're using Doom as a test bed, but actually it can be applied to any system and any problem. So what game agent provides? It provides strict control loops. So we have fixed tick rate. So 65 hertz in Doom ensures deterministic scaling. So we have complex state transition. So we're using here finite state machine-based NPCs with spatial awareness. We use real-time feedback. So there's physics, collision, light of science. So with rooms actually limited in size. We don't interact to events out in other room or interact in events in the room where they are located, and so on. So the shared state substrate, so the world state accessible to all actors. So I'm acting in a game exactly the same way as another actor, like zombie or some kind of evil character running around. And we actually also support event systems, so because the observable, the time ordering, and their actions. So in classic software, system is basically simple. We have input, we have program, and we have output. But the agent system, we have state, agent, action, environment, and loop back. Okay, so it's actually kind of self-learning implementation. So why we're using Doom laboratory? So GZ Doom provides a mature, extensible 3D environment. So we use 35 ticks per second as a loop. We're using that script for custom actor logic. So basically, agents are implemented partially in that script, native language to Doom. We use sector line depth spatial system. We're building physics, collision. We do event handlers for telemetry. We do external control via standard in FIFO. So this is not standard Doom you can download and build yourself. It's actually patch Doom, so it actually has more way to communicate with outside world where we can plug our agents. So the contributions here is that we have this finite state agent framework written in that script. We have policy guard system. We're actually defining what agents can do and cannot do. We also have external Rust control plane. We also have MCP gateway integration so that, as a matter of fact, we can plug other systems. So Doom doesn't know that the agents interacted with it. The agents actually don't much care about the Doom itself. So it's actually two-way blind system, but it's actually working. And we also implement the agent cell framework adapter. Agent cell is actually this small, compact, fast-running agents framework designed for different reasons, but also for this one, for this game. So as architecture, All agents can be observable, so capture the structured events, attributable, so linked to specific agent or context, and reproducible, so through the world state changes. So this invariant guides us through architecture decisions so that we actually, the actions are distributed, so they're actually transparent to other agents, actions of one agent, transparent to actions of another agent. When I'm interacting with the agent, also my information being transferred to other systems. So it's two-way street. So in world state modeling, we say that the world state is structured into 5 layers, so per this design. So it's spatial state, where actors are fast, they're moving, the sector they're in. So the zone state is 4 zone types: safe, contested, quarantine, extraction, and so on, each with axis-aligned boundary. So we have agent state also. It's a finished state machine, row counters, target references. We have policy state, so that we can define the agent within the game, what it can do, cannot do, interact with certain objects or not events. We also have a scenario state. We can implement scenario and say, if something happens in these factors, A, B, C, D, what you can do, we can do this action or not. So this is all embedded into agent itself, so that's why it's not just a piece of code, it's agentic behavior. So we have zone manager implemented in the game, so when it's actually interacting with the game and see where agent sits, in which zone, and how it communicates with the entire world. So spatial reasoning with zones. So again, within the game, agents are actually sitting in certain rooms, or they may belong to this room, may belong to another, and we actually can tell them what they're supposed to do. They're supposed to be safe, they're supposed to be contested zone, quarantine zone, extraction zone, for example. So by listening to agents or implementing agents, we actually can change through our interface how a game behaves beyond the actual original scenario of the game. So agent perception, the most important part. So in this demo, so it's actually how agents see the world. So we have 3 channels. So those are in-game sensors. It's Z-script, 35 hertz. So it does check, site, distance, 3D, sector queries. Has zone context. So current zone types, eval actions, and agentic vision pipeline. This is the most important. So we have implemented so-called lens, so that we can see certain objects within the room and react to those, only to those specific objects. And this is called lens. So the lens are triggered, are tuned for certain object or action within this room or the map. So, and they are actual lenses, they interact with the LM. So there's LM broker, there's scene grabber with cooldown. We also have what's called a mosquito dog semantic cache. So as you imagine, we actually we don't have to send every time to external ALM what's going on with our system. We actually can cache it, and if we already find the answer or response to the problem, we can grab it back and see, so to save time, cost, and so on. So we have reply. So in terms of game, okay, so the game actually connected to outside world, and it actually talks to OpenAI GPT-4. And we implement here lenses, so basically whatever I see here, agents also can see, and they're actually attached to whatever object we have. We have about 1,000 agents. So as you see, there's in console, there was message like vision, busy zombie, scientist chainsaw, house bonus, and so on. It's actually trying to see and identify those objects, so in lifetime. Certain resources permitting, network permitting, and so on and so forth. It actually tells you that some request to identify object took like 3-5 seconds. Most of that is latency, so calling OpenAI, let's say, please extract this information from the image, understand it, return back what you see or don't see. So it basically sees here 2 characters standing in front, and it's from the back, it's trying to identify and says, okay, this is zombie staying with chainsaw. It's actually correct. This is another object, health bonus. It's somewhere hidden there behind. Over there, it's actually can see that too, and it's reporting back to me saying this is what you can do. We can see in this game, and we actually can react to it. We can write scenario about it, and interact with it through the agents. Okay, so it's actually fully playable. So these dots you see appearing is actually trying to show some approximate position where agents saw this particular object, like armor bonus or zombie scientists and so on and so forth. What actually can also see if this body or enemy has kind of transition in form or shape. So if we interact with this, it may lose hand, it may lose head, and so on and so forth, and it will be also identified and so on. So it's trying its best to understand. So with this vision lens, for demo, primarily scope is actually interaction with the actors. So within games, enemies and myself, player, we consider it actors. So it's actually usable. Yeah, usable. Let me see. So it's actually reacting to gameplay. So it's not static. So when I'm shooting something and scene changing, transitioning from one to another, it brings more zombies inside because I'm actually eliminating them and so on and so forth. So, and certainly when game changing so fast, we cannot get too many messages at the same time because it's a limitation of pipeline or actually bandwidth. So, but trying its best to understand the scene, what's going on, and report to us correspondingly. Whatever it can see affects the scenario of the game. And it's actually then changing how those enemies interact with us and what the feedback is and so on. So I'm trying just to show the object and see if it can pick it up, but there's not necessary in this environment in demo. It can do it faster, but actually doable. So we go back to the game a bit later. So the thing is that anything going on, any object, subject within the game, we can attach agent to it and see, okay, work with it. So it will watch, follow certain scenarios, react to it, change behavior, will move actors from one place to another. And so active and control through the agent. So we have two-tier vision. As I said, the vision kind of a big part here, two-tier agentic vision. So we have, through the vision, we create this semantic mirror. So in one tier is a chip observer swarm. So that script works the actor list at 7 Hertz, projects each actor to screen coordinates. As we see, it shows a location where it's seen certain subject, object. And so it's called ABS. And this also gateway picks that runs the observer, same through the actor, create different roles, idle, tracking, suspicion, alarm lost, and so on and so forth. It's basically this part doesn't have ALM, it's deterministic, but it's also ALM part, ALM broker swarm. It has 4 lenses, NDT, HUD, motion, zone. So 4 different agents through the broker. They see these lenses, so they actually filtering what they can see within the game. So they're using the same screen as I see, and it's just working with that, trying to extract information. And so why we have two-tier agentic vision? Because one is faster, another one is slower. So obviously ALM is slower, and we separate whatever we can do without ALM. We push through first tier, whatever we have to go through the second ALM tier, we push it through the ALM, and it's 2 different aspects of the game. So I will show it in control plane. Let's see if it comes up. Yeah, so this is our control plane. It's our agentic system. So as you see, this is 1,000 agents. They attach to consumer swarm. So this actually, we have two sort of agents. This one for observer and this one for LLM. So for LLM, we have 1,000 agents. So it doesn't mean they're actively running all the time, but they, depending what they do, what kind of scenario they have, what they're running. But they actually, so we can see all the agents, what they're doing, some tracking, some tracking, some tracking. We also have a broker entity. There's a broker entity up here. We actually have 4 of them, or three actually. So one broker is pickup, another broker entity, and third broker is manifest. The manifest is a special scenario I will talk about later. It's actually a game scenario implemented through agentic view, agentic vision. And pickup means it's a broker that coordinates messages, picking up certain things from the floor, like medikits, team kit, and so on and so forth, clips, or weapons, weapons. And identity is actually looking for those characters, understanding what they're about, what they do, what they do to the attack, they defend, and so on and so forth. So this provides information, feeds to the pool. This is semantic cache. So as I say, we're not necessarily each time communicating to OpenAI to understand something what's going on with our game. Something we saw before already, we're caching. And next time we found the same object, we retrieve from cache and say, okay, see, this was something before. So we will have to send all the time the same information to OpenAI for analysis. It saves time and costs. So basically, it depends how you play, but let's say typical map play like $2 cost with OpenAI cost. So this is our game engine, and that's actually twofold. This is ABC long, OBS, it's actually observer batch. And this is Doom bridge. So we have here STD in, we communicate to the agent through the Doom MCP gateway. MCP gateway exposes what our agents can do, what kind of service they support, and so on and so forth, what kind of tools. So it's actually, we can plug here any LM provider, or we can plug here another game, or we can plug another system and create similar application. So so you see those are agents. There are say over 1,059. Again, not of them running all the time. So and not all of them actually engaging with LLM. So it's a bit different agents, not what you use in Copilot. They designed to be light and fast. For broker functionality, as we see, we do capture, we do fingerprinting the hash, the enemy, we understand what the enemy is about. We do posts for the visions and so forth. So everything goes through the JPEG imagery, sent back and forth to understand the idea. Okay. Let me go back to architecture. Go back to architecture. Okay, so this is what manifest. I was saying there's a broker for manifesting. This is Agent Smith effect. You know, in the Matrix movie, there was agents. You always, if Neo comes to some sort of room, someone sees the Neo in the room, and the agent will manifest in this room to attack Neo so he can run away. Similar idea here implemented as example of such scenario handling. So we're actually seeing where the character, where I'm playing, in which room I am. And it's the agents working on manifesting of Agent Smith. They're watching where I'm going. And depending on sort of conditions described here, it's actually manifesting the enemy behind me or around me so that an enemy can attack me. So for example, I'm standing too long for a certain location. And game wants me to move, and they just put this character in front of me, behind me, and start attacking, so I'm moving. It's also, for example, I'm about to pick up certain weapon, like rocket launcher and so on. It's actually can see that I'm about to get it. And if I'm getting it, it's actually reading, putting me this enemy behind me or around me so that the enemy can attack me and certainly would not allow me to pick up this enemy, this weapon, and so on. Or, for example, armor and stuff like that. So we have decision loops. So as I say, we implemented infinite state-based agents. So not necessarily they communicate to LM, but they have certain states like idle, patrol, they define 12 states: seek, engage, invade, regroup, collect, and so on and so forth. We can tell by using our vision, we can see our characters, our evil characters playing within the room, and we can assign certain functionality within those states. We also have 5 roles: guard, scout, medic, retrieval, and civilian. So not all of them used, but for example, scout or guard, we actually, as you see, I start shooting, they run away, they run at me, and start assembling and attaching. This is actually a reaction to what's going on there. And we also have tick, per tick cycle, means it's like in CPU, we have certain ticks, and each operation should take certain ticks. This way we control performance, we make sure that we're always moving forward and we don't pollute too much with the actions we don't need. We have actions of 9 types. So it's move, attack, hold, retreat, collect, escort, defend, and enter zone, and signal. So obviously for the Doom, it's clear. So moving one character to another room, attacking, holding, retreating, collecting, escorting, and so forth, and so on. So we have determinism and autonomy. So we have determinism in the way, so we have game loop, which is 35 ticks per second. It's fixed time step. We have state transitions, same input, same effort, same transition, so they don't change. We have policy evaluation. So we apply to agents a policy, what they can do, cannot do, and telemetry. We're actually exporting this information. And for example, to use it in control plane where we see what each agent does, so it's actually exposed. So we're autonomy, target selection. So as you see in this vision plate, agents, we say we should watch for a certain character, they will watch for a certain character. For a certain type of character, they will watch for a certain type of character, and so on and so forth. But target selection is absolutely freely defined. It depends what they got, what they find. We don't specifically tell coordinates. We have path planning, we have LM reasoning, so it's internal vision pipeline, which is varies per frame. It's, we don't have like response every another second. It could be different, and depending what we see, response will be different. So we do our actions observable. So we actually have structure. It's for 9 event, the events time, spawn, transition, policy blocked, policy rewrite, spotted target, and zone change. So it's all exposed through the JSON-L to SQLite to record this and find later. So they're available per agent. So if we have 1,000 agents, those structures been applied and created for each one of those agents. So we have attributes, and we can reproduce actual behavior. So the game's changing. Yes, this is correct. But obviously we'll have different response, like looking to LM. We can retrieve different, it's always can be a different response for them, what we see, what we cannot see. But it's always the same, what kind of policy we're applying and what we want to, what kind of scenario we want to execute. So, and it's all being exposed to the REST API, and we can retrieve it. So for system overview, there are 3-layer architectures, I said. There's game runtime itself. So we created FSM agent base class plus 5 row subclasses, policy guard, zone manager, and telemetry. For control plane, it's a Doom bridge, so it's actually export whatever communication happens between game engine and agents itself through the HTTP. There's a relay. We have policy engine. We have replay store. We actually can reproduce what's going on in the game later and try to replay and see what kind of other responses will be, because as we know, ALM game not necessarily plays exactly the same way another time, but we can actually say what kind of behavior we expect for certain characters and see how it plays back. So it gives us certain real-life factor, and we can simulate this kind of semantic behavior by reproducing it. And we have MCP Gateway. MCP Gateway is implementation of agent cell. MCP service, there are 3 MCP services, the warp provision policy, and we have rate limiting and tenant policies in MCP Gateway. So a bit code information. So FSM agent implementation looks like this. This is just one example. And it's written in game native language in that script. And provides actor and provide tick information, and actually what can do, cannot do. We see here policy check. So the policy means we can define what they can do within this scenario and enforce this scenario. So those scripts are actually compiled at the time when application being executed. So actually it can be runtime deployable. So every time we update or change them, we can push them at the time when game is running. So it's actually kind of GitOps sort of operation. So policy guard and runtime enforcement, similar idea. For policy guard, we can have permissible, standard, and strict enforcement. So three different types of policies. And we can actually switch from one to another, from permissible to more aggressive. So MCP Gateway is model context protocol, as we all know it. There are 3 MCP services implemented. Doom world is action execution, so move, attack, collect, and so on. There's Doom vision, so we can actually, where we are taking screenshots for basic screenshot snapshots for our vision to send through GPT. And this Doom policy when we're enforcing what each agent can do or cannot do, as I say. The gateway features, so we have session routing with infinity. We have token-based bucket rate limiting, so we're actually defining how much of our LM resources we're using. We're using timing policy, enforcement, semantic cache policy for repeated queries, and policy deduplication. It's typical for any kind of communication. Any application works with data, real-time processing, and so forth. So the implementation being used here called agent cell. It means each agent can run autonomously, has autonomous data and interaction with the entire world. This is the main adapter, again, written in Z script. It bridges agent cell, each agent with action modes, what happens in the Doom. And we also have multi-agent coordination. Agents actually communicate to each other through the internal game engine so that they know what they're doing. When I said this, I start shooting, they come together and try to attack, this kind of behavior. So this coordination mechanism also in place. So for infrastructure component, as I shown in control plane, we have control plane, Doom bridge, screen grab. So it's actually real-time capture of the screen, what's going on, used for the vision. You have vision watcher. It's a GPT-4 loop, but it's not necessarily needs to be GPT-4. It can be any other, including local. We also have game runtime and dashboard. So dashboard is React D3. For telemetry pipeline, we have ticks. We have telemetry itself, telemetry handler, events, replace, store, and SQLite. It can be different data source where it can be stored, but it's flexible, can be changed. So we have runs, events, and policy changes. It's all also being traced. So for the game to production systems, so what we see in the game, we have 35 Hertz tick loop, so in game. So in the actual production environment, agent schedule with fixed intervals. We have finite state transitions, so it's workflow state machines, so they exist in real applications. We have policy guard. It's a policy engine, so RBAC and so on. That's actually mapped to those real things in the real application. We have zone boundaries. It's authorization domains. So there's a lot of analogies with real-world applications where agents can be employed, not necessarily game-related. We have telemetry events, which is structured logging. We have replay store, which is audit trace. So whatever happens in the game, I can record and replay. Same idea in the real. If I want to replicate certain process, actual real design or application, I can do the same thing. That's called audit trace in that real application. For behavioral regression, this agent policy validation in CI/CD. So as I say, the scripting for agents that can be deployed in GitOps operation, in GitOps way. So if something changing, we deploy it and run basically in real time. So what this design is based on, there are many classical examples. So we're using substitution architecture from Brooks from 1991. It's ARQ-driven layer preemption. We have blackboard architecture. It's also gateway hosted pools. For example, we have observer, broker, swarm. We have dual process theory. So we have running two-speed system, slow system and fast system. For example, ALM is for our slow system, and for chip observer, it's a fast system, so that we keep up with the game. We have also loops for observer. So ARQ in this case is what we know from CPU. If a finite state machine running and have certain states, we actually can interrupt it and do something else, depending if we need certain action. And we have active model, as I said, for it's actually been a really long time since everything been implemented, and active model comes to us from Erlang. So two more additional slides for economics. So real numbers are that, let's say 16 days development, but it's not correct actually, costed like 10, 11 bucks and so on, this bypass run and so on. So what I'm trying to say, we can, it's not really expensive to run it, but depends on what kind of map we have. So as I say, each run through the map will cost like $2 today with the current implementation. Because we're using cache proxy, semantic cache proxy called Mosquito Dog, and this kind of implementation is custom designed for this demo. It makes us 3 times cheaper than speak directly to ALM. But it's actually also kind of a research topic because this kind of semantic caching proxy is still not entirely developed to final design. And we're actually embedding traffic. We can use for the caching actual local ALM. We can run Olama, for example, and instead of sending to remote OpenAI, we can use through the semantic caching proxy Mosquito Dog, talk to local ALM. Also will save money. So for hardware, so this laptop is really basic hardware, nothing special. But even this hardware can support acceleration. So at the same time, we're running as 1,000 consumer ticketed agents. So the way we designed them. We also can run Olama at the same time. So not necessary requests going directly to, as I said, to OpenAI. They actually route it to local LM first and see there's a cache, there's local LM, and then there's external LM. So we can actually granularly define where our request is going so we can better control. So there's a capability to run this kind of design up to 1 million of this kind of small finite state machines in a CUDA. So and then it will be also the possibility to improve performance of the entire game. So what this presentation is about is that agents are semantic mirrors. So we can have a structured twin with a chip per actor finite state machine. Semantic enrichment via LM brokers, and LM is meaning abstraction engine, not planner. So game engines provide engineering discipline. So they have control loops, state management, event systems, and exactly what agent systems need. We can make agents observable, attributable, and reproducible. So this invariant guides architecture decision for any agent system. So we have policy guards at the autonomy boundary. So within each state machine or agent, we actually have a policy, and this is autonomously running. We don't have to enforce it from outside and enforce from inside. So we can have simulation as foundation, means that we can validate. So if, again, as I said, we can plug this agent system to anything we want, no necessary game. It can be this game, another game, or real-time process of phenomena, and can replicate semantic links between them and reproduce and replay. So it's actually plays a significant role later on in different industries, including in the industry where I'm from. So, and also we provide cost-aware routing as architectural feature. We have semantic cache, local model, and tiered escalation belongs to design, not to budget review. So it's actually, with semantic caching, it's actually a big deal because we not cache really texts. We're trying to cache images. We're trying to understand semantic within the images because we're building vision with lenses, and this is where semantic caching comes in. So as resources, again, this is GZ Doom, Rust, MCP implementation, and React DM for the 3. So it's basically entire presentation. If you'd like to, I can show more gaming, or you can ask specific questions if you like. Yeah.
Does it mean that LLM kind of empowers other NPCs to play against the LLM in real life?
You can.
It's like a hard-coded logic, you can flag the LLM and kind of play against
It's LLM and agents running on top of existing game design. So through the LLM, through agents, we can enforce certain behavior. So in addition, it's not what's hard-coded in game engine. It's actually we can move characters, react to whatever happens through the vision. So vision is in this demo is primary information input, but it's actually not only. We certainly can read directly from game where each character placed and put it to LLM and react. But in this case, I use specifically just vision demo so that I see what I can see, and also agents attached to this game also see through the same screen. And we can tell the agents what objects here to see, to watch. So to watch exactly these characters here in front, or watch certain bonuses we can pick up, or watch for strategy. For example, you see they're running at me, they assemble, they're going from outside, from another corridor and coming here. So it's also enforced through LLM and through agents, okay?
So the behavior of NDC controlled by LLM?
Yeah, yeah.
So it's kind of like, if you move to the metrics analogy, it's kind of like an architect.
Yeah.
So you play against.
Yeah, you're playing against artificial intelligence, in a way. But it's certainly slow. You see this detection of object takes like 5 seconds, maybe 3 seconds, maybe 2 seconds. And also it depends on how complex we want to be. But this analogy I'm using, like Agent Smith, is actually a real analogy. So that game that's brain with 1,000 agents running here, this looks like actual brain. They're watching you through the same lenses, and they're trying to understand what they do. Those agents here, this is bulb, this bubble here, is blue, and we just tell them what they're supposed to watch, but what they're actually watching is up to them. So, and what kind of results they receive from that image depends what LLM will return to them. And they have the policy, and they may have scenario, and they see it doesn't match to that scenario or not, and this reasoning goes to LLM, and comes from LLM, okay? So it's not deterministic. So it could be anything. They can attack me directly, can go around, so we can actually play with it. Depends on how complex we want to have this LLM reasoning. So if I want to just detect certain object within the room, it's one thing. If I want to think them like a strategy, so that depending on not the simple room, but maybe they can walk around behind me and attack from the back, we can do this too. But it will take longer for reasoning, because we need to provide a context to it, and we say, this is the map, this is the room A, B, C, and so on. You can move from this room to another, and so on. But this specific depends on, say, budgeting, depends, because we can bombard with request LLM and see how keep up. So the problem is not really game engine, the problem is how LLM can respond, how fast. Yeah, but it's actually right. It's kind of building metrics. It's using UIs to see. We can actually see, again, we can redirect game, or we can use UIs and see where you're going and try to detect where you're standing in which room, and depending what you see, we'll put some kind of agent and we'll attack you. So Agent Smith is actually correct analogy here. And the metrics is correct, yeah. More questions? So we have ticks, we have ERQ here, the interruption, so that each agent has kind of workflow, ABC it follows, but ERQ actually can stop agent and say, you don't have to follow this workflow anymore because something happened, like some reaction in real life happened, I mean, in the game, and it actually affects your reasoning. And this for that ERQ is used for kind of analogy. Again, this is caching proxy. This is our MCP gateway. We can plug this MCP gateway, if you like, to Copilot, and from Copilot control the game. It's also possible. So just through the prompt, say, send this agent to that position and go to that position. Something like that. In terms of game, so the guys actually at Project Brutality, they did a fantastic job, so I'm not really claiming their work. The part here is not graphics, it's not some kind of visual effects. It's about really bringing this agentic sort of mind to the game so that we can react in real-time possibility, but it doesn't work in real time. There's a clear delay, and you see that for it takes time for reaction. We will print in the console saying, I see this zombie with chainsaw, this zombie with something. You see, vision zombie comes up, zombie scientist, helmet zombie man. So it can look at an object and refine what it can see. So it actually can be the same object, but because you're running around this object, it can see better and say, okay, this is actually zombie helmet. Okay, this is actually zombie's helmet and the gun, and so on and so forth. They actually understand better. It's following the movement. I also sees like bonuses, armors, as I said. I can see doors, switches, keys, anything. There's no sound interaction. As a matter of fact, as we do vision capture, we can actually capture sound, and depending, so because those demons, they actually make noises, like specific noises. Each demon has their own noise, and we can understand from noise what demons are in the room, and also react to this. Also, the player itself. So, for example, when some started shooting some location, also can be used to affect action and what the actors do in this particular game. As you see, we have here reaction time. So some requests took like 13 seconds. So unfortunately, it's a latency of LM, and remote LM is in OpenAI, but it's also, so we're trying to bring in between this semantic cache. But semantic cache not always works, because if something new comes in, so for example, I had previous room where I scanned the room and I already cached the room, and when I'm moving around the room, it's actually understand and retrieves result. But if I go outside the room, this is new room, and doesn't have a cache, it needs to get this information from LM first, and if it's so slow, it cannot get it on time, so then it takes 13 seconds. It's a first map, I think it's Doom 2, but it really doesn't matter. So those characters, they come from Project Brutality, they're not my doing, just in case. Okay. It also detects when, for example, something happens to that character, I'm sorry to say, some hand shoot off, some leg shoot off. It actually will tell you that, okay, this is zombie, but without hand or something, and so on. It actually detects those changes and can give you more specific information. Yeah, so more questions? Yeah. Drug discovery. Yeah. So you can imagine a molecule, it interacts with another molecule and so on and so forth. So we can research, it's called digital twins. We can replicate behavior of a certain substance or molecule or some chemical substrate and use it for to better understand. For example, drugs supposed to be created for specific patients. So drugs have side effects, right? So work for one guy, it doesn't work for another. So if we can minimize the side effects, we need specifically designed drug in a way so it's usable for this guy specifically, only for him. So how to do that? Simulate. So that we basically have kind of body simulator, but this actually exists in different domains. Body simulate and say how this molecule will perform in that body. This also exists for operations. So certain operation needs to be done on human body, and before they perform in real life, surgeon actually basically plays with the system, like would be this operation successful or not, what is the best procedure, how interact with the human bodies, how to get a cut, and so on and so forth. So it's actually a real thing, it's actually happening, and more, and this digital twins actually a big topic, big subject today, and it's being actively researched and being actively implemented. So yeah, so actually we have real life application. Sometimes it's connected to visual reality, so VR, so you don't interact through manipulator buttons. We actually can move your hand, so you can actually develop certain manipulations with your hand, so it actually do right thing when it comes to actual operation. So surgeon can try certain methods before doing the cut in real life for real people. So it's actually also part of this kind of application. So in this case, it's been plugged to the game, something what could be, it's not necessarily one-to-one what's actually used in some projects in production, but it kind of made after this idea, even so this complete new design on application, okay? So done for this demo. So this is not the actual DOM, it's actual, I patched this DOM because original DOM has no ability to communicate to outside world so much. So it's patched DOM, and this entire broker pool and everything, and Agentic engine can run on cloud separately. So imagine you have DOM running on your local machine and communicates to the cloud where this entire brain is running. So it's actually completely doable application. Yeah, more questions? Yeah, okay, thank you. So, hope it was interesting. So if you have more questions, you can contact me. Find me on the internet, on LinkedIn, and ask for more. Okay, thanks.